All right, let's jump right in. We are living in a world that is absolutely built on logistics. I mean, think about it. From the phone in your hand to the food in your kitchen, pretty much everything you own has been on a heck of a journey. But how do companies manage this giant global puzzle of getting things from where they're made to where they're needed, all without going broke? Well, today we're going to dig into the really cool math behind that exact challenge. I mean, really think about it for a second. The moment you click Buy Now, you're kicking off this incredible chain of decisions. A company with, say, a bunch of factories and warehouses has to figure out the single cheapest way to get that thing to your doorstep. Do they ship from the closest warehouse? Well, what if that one's running low? What if the shipping route from there is way more expensive for some reason? This isn't just a small problem for one company, it's a fundamental challenge for our entire global economy. Okay, so here's the exact puzzle we're going to solve together today. Imagine we've got three sources, maybe factories, listed on the left there, A1, A2, and A3. And across the top, we have five destinations. Let's call them stores. Now, all those numbers in the grid, that's the cost to ship one single item from a factory to a store. So, for example, it costs $5 to ship from factory A1 to store B1. Our mission, should we choose to accept it, is to figure out how many things to send on each route to satisfy everyone's demand for the lowest possible total cost. Now, this whole thing we're looking at, it actually has a formal name. It's called the transportation problem. It's a classic puzzle in the world of operations research. And the goal is beautifully simple, really. Find a shipping plan that meets all the demand, doesn't exceed the supply, and, this is the important part, does it all while minimizing the total cost. It's all about finding the smartest path. To solve it, we just need to keep these five things straight in our heads. We've got our sources, our destinations, the supply that each source has, the demand that each destination needs, and, of course, the unit cost for every single possible route. With these pieces on the board, we can actually start to build a solution. So, how do we actually start filling in that table? Let's kick things off with the simplest, most direct approach you can imagine. It's called the Northwest Corner Rule. And honestly, the name pretty much tells you everything you need to know about how it works. The best thing about this method is just how simple it is. It's fast, it's super easy to do, and it gets the job done. But, and this is a huge but, it has one massive blind spot. It completely, totally ignores the costs. It's designed to find a solution, any solution, not necessarily a good one. It's kind of like packing a suitcase by just grabbing whatever's closest to you first. The logic is, well, it's about as simple as it sounds. You literally start in the top left corner of the table, the northwest corner, and you shove as many units as you possibly can into that box. Once a factory supply is all used up, you just move down a row. Once a store's demand is met, you move one cell to the right. You just kind of snake your way through the table until everything's allocated. Okay, let's actually do it. We start in the top left, A1 to B1. Store B1 needs 40 units, and factory A1 has 80 it can send, so we give B1 all 40 it needs. Great, B1's demand is met, so we're done with that column. What's the rule? When a column is done, we move right. So now we're at A1 to B2. Store B2 needs 20. Factory A1 still has 40 units left, so no problem, we send 20. And we just keep following this logic. Move right when demand is met, move down when supply runs out, until the whole table is full. And this is the final shipping plan we end up with. Notice we didn't look at the costs even once. So, what's the bottom line? What's the damage for this simple but dumb plan? Well, when you multiply all the units we shipped by their costs and add it all up, we get a total of 1,090. Go ahead and burn that number into your brain. It's our benchmark. It works, sure, but the real question is, can we do better? Oh, you bet we can. And that brings us to our second approach, Vogel's approximation method. Now, this one is much, much smarter. Instead of just blindly starting in a corner, it actually looks at the cost to make intelligent moves right from the get-go. The whole idea behind Vogel's method is to avoid making big, expensive mistakes. It looks at every row and every column and basically asks, hey, what's the penalty if I don't use the absolute cheapest route I have here? By finding the biggest potential blunders, the routes where the second best option is way more expensive than the best one, it prioritizes dodging those costly errors first. The logic here is way more strategic. It's kind of like playing chess. First, you calculate a penalty for every single row and column, and that penalty is just the difference between the two cheapest shipping costs in that line. Then, you scan the whole table and find the biggest penalty.
That's your most urgent problem to solve. So you go to that row or column and you allocate as much as you can to its cheapest cell. Then you just recalculate the penalties and do it all over again until the job is done.
And what you'll notice right away is how different the solution looks. It's not a neat little path from left to right anymore. The numbers are jumping all over the board. And that's because the logic is so much more strategic. For instance, the algorithm looks at row A1, sees its two cheapest routes are $5 and $6, so that gives it a penalty of 1. It does this for every single line, finds the one with the biggest penalty, the biggest risk of overpaying, and satisfies the cheapest route there first. It might look a little chaotic, but there's a powerful cost-avoiding logic at work. And what's the result of all this strategic thinking? The total cost for this shipping plan is just $860. I mean, wow, that is a massive improvement over the simple Northwest Corner rule. And all because we took a minute to think ahead instead of just jumping in. All right, it's time for the showdown. Let's put these two methods side by side. On one side, we've got the simple, fast, but totally blind approach. And on the other, we have the strategic, cost-aware method that takes a little more brainpower upfront. This really breaks it down perfectly. The Northwest rule only cares about where you are on the table. It's pure mechanics. Vogel's method, on the other hand, is focused on the actual dollar amounts and the consequences of your choices. So one gives you just a feasible solution, while the other gets you a really good initial solution, something much closer to the best possible answer. And honestly, this chart just says it all, doesn't it? That is not a small difference. The bar on the left is that high cost from our first simple method, and the bar on the right is what we got with Vogel's method. That huge gap between them, that's pure, cold, hard cash saved. So what this all boils down to is a 21% cost reduction. Just let that sink in for a moment. We didn't build a new factory, we didn't find cheaper trucks, we just used a smarter piece of math to make our initial plan. That right there is the power of optimization. And that leaves us with a much bigger question, doesn't it? This was just one little logistics puzzle, but this exact same kind of thinking can be applied almost anywhere, to traffic light patterns in a city, to managing hospital beds, to making our energy grids more efficient. If a smarter starting point can save 21% right here, just imagine all the untapped efficiencies that are just waiting to be unlocked all around us. What other complex systems in our world are just one good algorithm away from being fundamentally better?